Last class, Wednesday, we learned two things, two coordinate system. One is called Cartesian, right? Another one is called polar coordinate system. Okay, I want you to close your notes, kind of just try your best. Think, what are the equations we learned on the Cartesian coordinate system? What is the equation? Okay. What's the equation for, what are the three equations? The name of the three equations. One is for what? Position and velocity and acceleration. Okay, what's the equation for position? Remember that? What are the unit vectors for Cartesian? I and J. And what are the equations for position? Xi plus yj, right? It's pretty easy. Xi plus yj. Is this right? Could someone correct my mistake? I made a mistake on purpose. R, what's wrong with R? Perfect. This, if I write, all right, this, if you have this on your homework or exam, I'm sorry, I take all the points off. Class, in this class, you must know the difference between scalar and vector. Writing R like this is a scalar. This is not what you want to have there. Instead, you need to have that either a bar or arrow overhead to show that is a vector. All right, what's the next? Velocity. What's the equation for velocity? Just take a dots, right? Take the derivative. X dot I plus Y dot J. So what's the equation for acceleration? Take two dots, double dot, plus Y double dots J. Good. That's Cartesian is pretty easy. All right, now let's move on to path. Path coordinate system. What are the equations we learned for path? Velocity. What's there? Can someone tell me what's the expression for velocity under path? What's a unit vector for path coordinate system? ET, EN. So for path, just tell me, should I have an ET here or EN? ET. So we have something ET. What is that something? It's a V, just speed. For acceleration, for path coordinate system, we can have something ET plus something EN. Okay, what's in front of this blank and this blank? Yes. Let's start with the first blank. What's there? It's a V dot. Is that right? And on the second blank here, let's heard square, something square, V square over rho. What is rho? Radius of curvature. So make sure you write it down. Rho here is the radius of curvature. Okay, now you can open your notes. Make sure you have those on your notes. And rho is the radius of curvature. Okay. Now another test for you. If we have a particle, let's call this P. P is moving along this trajectory in this direction. If we want to use path coordinate system to describe the motion of this particle, how would you put the path coordinate system on for this particle? where would you place your ET and EN? ET. If you use your finger to show me which that way, that's ET. How about EN? Yeah, that's EN. Okay, yeah. Where's ET then? This direction. Okay, that's correct.
So your ET and EN.
Can someone tell me? What's your name again? Austin. Austin. Austin, you're right. This is the way you should put ET and EN. But I want someone else to tell me why ET is pointing to that direction. The tangent to the path of the line. It's tangent to the path of the line. We can, if we want to have a tangent direction at that point, that can go either go that way or that. But why it's pointing to right instead of pointing to that direction? Yes. So ET must point to the direction of velocity of that particle. Particle P is moving in this direction. So that's why you have to point in the same direction. All the particles move. And why EN has to point into that direction? Can someone tell me why EN is there in that way? Why EN can point into that direction, that direction, that direction? Go ahead. Point to the center. Yeah, that's to point into the center of curvature. And the center of curvature can be easily identified. Just look at this curve is concave of the other word of that one.
All right. Okay, those are the recalls of what we learned last time. And we have one more coordinate system we need to talk about today, which is called, what's the name? Do you remember? Polar, yes. Okay, from my experience, this is students' favorite coordinate system. Believe me, you're gonna love it. All right, so we just did example on how we draw a coordinate system for path particle, path coordinate system. If we have a kind of the same particle, P is moving, let's say this direction. If we want to use polar coordinate system, then first we need to have a kind of origin where's that polar coordinate system is. If I pick this is my origin O, I want you to compare the polar coordinate system with Cartesian coordinate system. Cartesian coordinate system, you have a fixed origin and fixed direction for x and y. Here for polar coordinate system, we have a fixed origin here, but direction for its x and y can move, can rotate about the origin. Here we don't call it x and y, we call it ER direction and E theta direction. So let's use a different color here. Your ER, the first unit vector here, it's pointing to the direction of particle. Oops, I think I'm way off here. Redraw this. Yes, ER. ER is pointing to where's that particle is, from the origin pointing to the particle. And E theta is another unit vector. Like we mentioned previous. Now we know ER. Do you kind of know the direction of E theta? E theta and ER, they must what? They have to perpendicular to each other. So E theta can either go that way or that way. And which way? In order to answer that question, you need to know the angles. Let's draw a horizontal line as a reference. This point is A. The angle between OA and OP here is theta. Oops. Okay. So this is the angle theta between the horizontal line and this vector r. Imagine after a few seconds, particle P will move around this path, will be somewhere around here. Now, what's the angle of theta going to be at that? Should that be smaller or larger? Smaller. So E theta must point you to the direction of increasing of theta. If particle going that way, E theta is decreasing. Then we have to draw our E theta at the increasing of theta. Okay. This is the direction of ER and E theta. Keep that in mind. Just want to show you an example. So if your particle P is at another moment, it's right there. And like I mentioned, polar coordinate system has a fixed origin. So the origin will be always here. But at that moment, your ER and E theta need to rotate for a certain angle so that your ER is pointing to the particle P and your E theta is still pointing to the direction of increasing theta. So at each moment, you're going to have a different angle of the coordinate system, if that makes sense. So I will use blue color to show you if at point, let's call this point A, point B. At point B, your coordinate system is going to look like this. So this is your E theta. This is going to be your ER. That makes sense. So keep that in mind. ER, E theta is changing, always changing to track the particle. That's why this course is called what? What's the title of this course? Dynamics. All right. Okay. So this is how we set up ER and E theta. Now let's look at math. For polar coordinate system, we do have three equations: position, velocity, and acceleration. For position, the position equation for on the polar coordinate system is pretty easy. It's just r, which is the distance from origin to the particle. So right here, r. Oops, sorry, it's not showing on the screen. So the r is the distance from origin to P, and the position vector equation for polar coordinate system is r times E r hat. And for velocity, what do we get from r to E? Take a dot, the derivative. You do that. That is dr dt. This will give you expression for velocity, which is r dot E r hat plus
R theta dot E theta hat.
I know some of you, not all of you, maybe one or two of you are very interested in math. Want to figure out, have a question mark in it. Professor, how do we get from the derivative of this guy when we end up with this equation? Now we have theta and u theta. What is going on there? All right, if you're interested in that part of the math, and can come to my office hour, we can spend probably 35, 40 minutes. I will show you step by step how we get there. But if you're, for most of you, I guess that's the case, don't really care how we get there from here. Just remember this is the expression for velocity for the point system. Just curious, how many of you are interested in that 30 minutes, 40 minutes explanation? Does that mean? Feel free to come to my office and show you that.
But now you can, instead of velocity equation, we have R dot. Keep that in mind, it's different from R. It's a derivative of the distance of the radius. And R times theta dot. What is theta again? It's an angle. What happens if you take an angle with a dot? You take derivative of angle with respect to time. What does that mean? What does that mean? Let's use this as example. If S is the distance, what is S dot? You use distance or position, take a dot. What is that? That's velocity, that's speed, right? How fast your distance changing, that's speed. Okay, now I want to ask you, if now we have theta, which is angle, you take a dot for theta, what is that? Angular velocity, that's the speed of angle, right? And later on in probably chapter 3, 4, 5, you will see we use omega for angular velocity. I think in this chapter, we just use theta at a dot. That's angular velocity. Okay. Now let's look at acceleration. What's the equation for acceleration in polar coordinate system? Same deal, take a derivative of v dt, and I will skip the 40 minutes math derivation. Now you have the expression r double dot minus r theta dot square times er hat plus r theta double dot plus 2 times r dot theta dot times e theta. All right. Like I said, I promise you're gonna love this. Don't you love this equation? Beautiful, right? Oh, believe me, you're gonna use this over and over again, even during the last 2 weeks of the semester. So that's kind of the nature of the course. All the equations you learned today are going to be used over and over again during the semester. And the good thing is, you don't have to memorize this. Believe me, I couldn't even remember. If you want me to write this again on the whiteboard, I probably got it wrong. There's too many equations in this book. I couldn't remember every single one of them. But you have the book, you have your notes. You can always refer back to your notes or book. That's what I did.
And I write, want this equation, I know it's in chapter 1AB, that page. I go there, double check, make sure I have the right equation. And for your exams, you are able to have a cheat sheet to put that equation on your cheat sheet for your exam. Just remember, keep that in mind. Make sure you copy the right equation, correct equation. All right. And believe me, this is definitely not the longest equation in this course. This is the entry level. All right. Now let's look at what's going on here. Instead of acceleration equation, we have our double dot. If you take a distance, one dot give you velocity, speed, kind of velocity. Take another dot, that give you acceleration. All right. We have a theta double dot. Wow, that's kind of the acceleration of your angular acceleration. And just keep that in mind. If you want to use acceleration equation, make sure you have the right, like our double dot. Some of them are single dots. Make sure you copy the right equation. Okay. So far, we should have three coordinate system: Cartesian, polar, and path. Which one is your favorite? It's polar, right? No? Not polar? Okay. All right, now it's time for some practice. Now we have all the tools. We want to know how to use them. If you have book, I want you to take out your book. Find the example 183 on your book. If you don't have a book, make sure you get a book. Next week. Whoever you have the book, turn to the page 183. I don't know which page is that. And I need a volunteer to read that problem to the rest of the class. Most of the
Given a jet is flying on the path shown below with a speed of v. At position A on the loop, the speed of the jet is v equals 600 kilometers per hour. The magnitude of acceleration is 2.5 g, and the tangential component of acceleration is k sub t equal to 5 meters per second squared. And wants you to find the radius of curvature of the path of the jet at A.
Okay, thank you. So we have a jet problem. Jet is flying in the sky, and at this point A, we know some speed and acceleration about this jet. So in your homework, I would like you to do the same thing, is to always write what are the givens. So for the givens, we have it's at position A. So everything is at position A. It's under this condition. Speed of this jet, it's 600. Make sure you add units. Kilometers per hour. And another information we know is called the magnitude of acceleration. Equals 2.5 g. G here is the gravitational acceleration. And this is called magnitude of acceleration. Another given we know is AT, which is the rate change of speed of this jet. It's 5 meters per second square. This is called rate change of speed. And those are all the given informations we know. In this problem, we want to find what is the radius of curvature, which is rho, radius of curvature. Okay, let's go through all the given conditions here.
Speed. Remember, that's a scalar. What is this guy? Is that a scalar or a vector? This one. You think that's vector? Raise your hand. Scale. How many of you think it's a scalar? Raise your hand. Never mind. It's an A with 2 bars. Right. That's called magnitude of a vector of velocity. If you see the word magnitude, there's 90% of chance it's a scalar. If this is a scalar or vector, it's a scalar too. If you don't see that overhead bar or arrows, they're all scalars. Here, even you have this overhead bar and arrow. You have 2 bars, that means it's magnitude, so that's a scalar as well. Here we want to find rho, radius of curvature. All right, so what? We learned 3 coordinate systems: Cartesian, cat, and polar. Let me tell you, you want to use one of those coordinate systems for this problem. Which one would you pick? If you think it's cat, raise your hand. If you think it's polar, raise your hand. Anybody would use Cartesian, raise your hand. All right. So for most of the homework problem for this chapter, for this section is you need to decide which coordinate system you want to use. And to determine that, you need to read through the given conditions to find some hint. Usually, then the problem will give you a good amount of hint to tell you which one to use. Let's first look at some keyword here. What is this? Rate change of speed. Where did we learn that word, that phrase? Under which coordinate system? Path. And what is this here, this guy? Radius of curvature. Where did we learn that? Path. Yes. You see that? So this problem is begging you to please just use path coordinate system. Right? Okay. Under path coordinate system, we learned 2 equations. One is velocity, one is acceleration. Which one would you use for this problem? Check your notes, and which one would you use? The acceleration equation, right? We have so many things we know that come from that acceleration equation. Now I'll give you 2 minutes. You can talk with your neighbors or work on your own to see how would you solve this problem. Now we know you want to use path coordinate system. You want to use the acceleration equation. Or if you think, try your best to see how to solve this.
Okay, let's look at this together. All right, this is the same deal for your homework example. So once you have the given and find, now you need to have solution. The first thing in the solution is define what coordinate system you want to use. So as we discussed, we want to use path coordinate system. All right, once you define that, I want you to redraw that figure, the jet and the path, and to put unit vectors on your particle. How would you put the unit vectors of path coordinate system, which is ET and EN? Now, let me draw this on the board and you tell me where I get it wrong. So what's wrong with this? Anything wrong with it? ET and EN.
Each of them should be facing the way because that's the direction of the jet. Even this point of the mark. Yeah. Should it go that way? Yes. Okay. Change that.
Okay, so is this right? Okay, all right, this should be ET. And let's change this to EN. Now, what's the problem? Yeah, EN has to point into the center of curvature. So make sure you have the right direction for your unit vectors. EN, ET. Okay. Now we can use the equation from path coordinate system. We want to use this acceleration equation. Right? From the notes, the acceleration equation for path coordinate system is v dot et hat plus v squared over rho en hat. Okay, let's look at this. And one question I have for you is, since in the given, we know the magnitude of A, which is 2.5 g. Hey, can I do this? Can I just write 2.5 g equals blah, blah.
Can I do that? And just use that for my A? No, can't. Once again, this is acceleration. Do that over path arrow. That's a vector. You can't just use that number for this vector. All right, that's
Something to keep in mind. So we can't do that. Do we know anything about this v dot? This v dot, v is speed. Take a dot, it's change of speed. We do know something about that. So the rate change of speed is 5 meters per second square. So we know that. Okay. Do we know anything about v? V here is 600 kilometers per hour. 600 kilometers per hour. But this is not the desired unit we want. Everything else is in meters and seconds. This is something else. So you want to equate the unit to meter and second. This can be converted to 600 kilometers an hour times 1 hour, 3,600 seconds. Now you convert a kilometer to meters. That's 1,000 meters per 1 kilometer. From here, end up with 500 divided by 3 meters per second. So that's the V with the correct units, right? Okay. And rho here, it's the unknown we're trying to solve. So we need to solve that. How do you relate the magnitude of acceleration? How to use that information? We definitely need to use that. Yes. So whenever you have a vector, for example, this is a vector, A plus something, B plus something, theta. How do you find the magnitude of the vector? If this G and through you off, think about something I plus something J. How do you find the magnitude? Square of both components, and you take the square root, right? Same deal here. So if I want to find the magnitude of acceleration, I would take the square root of the first component, which is v dot square, plus the square root of second component, v square over rho square, and take a square root. This is how you should find magnitude of a vector. Square root of sum of the squares for each component. And we know in this problem is given the magnitude of this acceleration is 2.5 g. G here is the gravitational acceleration, which is 9.8 meters per second square. All right, now it becomes a very simple math problem. All right, if you look at this whole thing here, we know v dot, we know v, we know this side of the equation equals 2.5 times 9.8. Rho here is the only unknown. So this is not a dynamics problem anymore. It's just simple calculation. Can you solve this? Can you solve this equation with one single unknown? I would take a square on both sides of the equation. Right? Get rid of this square root. I'll take square on this side. Then I would put this v dot square on the other side. Take this one side of the equation. Take square on both sides of the equation to get rid of that power there. And some manipulation to solve for rho. So, okay, rho to v square over rho square equals 2.5 times 9.8 minus v dot square. Take another square root on both sides, end up with v square over rho, those 2.5 times 9.8 v dot square. Okay, then I can find rho. Let's put rho on one side of the equation. V square over 2.5 times 9.8 square minus v dot square. Okay, if my math is correct, and this will give us the value of rho, which is about 1157 meters, if my calculation is right. But this is how you find the radius of curvature for this problem.